Hello. In the next roughly 30 minutes, I will give you an overview of my research, which primarily aims to support modern spatial applications with efficient data management. Spatial data is core to many scientific and analytics applications. Here on the slide, I'm showing you 3 example applications that have motivated my work until today. Neuroscientists built 3-dimensional brain atlases that capture the shape and properties of different brain structures. City planners and other officials rely on spatial urban datasets to make more informed decisions. Finally, there are thousands of orbiting satellites that capture valuable information about our planet. Now, analyzing spatial data in these applications is very challenging for several reasons, but I would like to highlight the following 3. We are dealing with high data density, complex geometries, and also there is high data heterogeneity. So my research aims to tackle these challenges by developing efficient techniques for accessing and then subsequently processing spatial data. So the techniques that I develop include index structures, spatial approximations, and query processing algorithms. In the rest of this talk, I'll go deeper into some of these techniques, and I will focus more on applications related to urban planning and Earth observation. Urban planning is not a simple process because cities are complex environments that are shaped by multiple factors. Any location in a city may have all kinds of information attached to it. There is, for example, information about the infrastructure, like taxi activity, or about the environment, that can be the weather conditions or even the levels of noise pollution. Finally, social media capture the opinions and interactions of the citizens that live in a city. The available information can also be pretty detailed. For example, taxi records have different attributes, such as the pickup and drop-off time of a ride, the fare, the tip, and the number of passengers. All this complex information is usually available publicly in the form of numerous urban datasets that are published by governmental agencies. Now, analyzing these datasets presents a unique opportunity to understand the dynamics of a city, identify problems, and test the feasibility as well as the impact of potential solutions to these problems. To analyze these datasets and the correlation among them, city planners turn to visual analytics systems. That way, instead of looking at numbers, they look at colors on a map, as you can see on the slide, while they can compare multiple datasets in just a single visualization. Specifically here on the slide, you see a heat map visualization on your left-hand side that shows the distribution of taxi pickup locations over the different neighborhoods in New York City. The visualization on your right-hand side allows you to compare multiple datasets over different neighborhoods. Each dataset here is represented as a vertical axis, so you have a dataset of reported crimes, noise complaints, etc. And each neighborhood is mapped to a red line that traverses across all the axes and shows quantitative information about each dataset. For example, here the highlighted red line corresponds to the Midtown neighborhood of Manhattan. Just by looking at the visualization, we can see that this is the neighborhood with the highest number of reported crimes. Now, these visualizations look nice and they are very informative because they contain a lot of information that's very easy to grasp. However, to make them truly useful, we also need to be able to compute them quite fast so that the different analysis can be performed in a smooth way. To build these visualizations, visual analytic systems rely on what we call spatial aggregation queries. These queries partition the data in different regions and then compute summarized aggregate information for each region. This is the query that is issued by the visualization system in order to compute the heat map that I just showed you on the previous slide. It takes 2 datasets as input, the taxi rides and the neighborhoods in New York City, and then selects a subset of the rides for a selected period of time, which is January 2009. Then it maps each pickup location of a taxi ride to the neighborhood that contains it. This mapping operation from the pickup location to the neighborhood is what we call a spatial join. Finally, in the very end, it computes an aggregate information, in this case is the count of all the rides that had a pickup location inside each one of the neighborhoods. So for each neighborhood, it calculates the count of rides that started from that neighborhood. Now, let's zoom a little bit into the spatial join operation. This spatial join is performed in two steps. The filtering step uses a rectangle, which is shown in blue, to approximate the shape of the polygon and identifies all the pickup points contained inside this rectangle. The refinement step performs a point-in-polygon test for each point found in the filtering step to determine if it lies within the actual boundaries of the polygon. Any points that are outside these boundaries are discarded, and you can see the discarded points in this example with red color. Now, real-world regions are complex. They consist of hundreds of vertices, and this makes point-in-polygon tests very time-consuming because each test takes time linear in the number of vertices of the polygon. In addition, the point dataset is very large, and this means we have to compute a lot of those expensive tests, and overall, as a result, the point-in-polygon tests are so expensive that existing techniques cannot answer spatial aggregation queries in real time. As a result, they cannot fulfill the requirements of visual tools for interactivity. To solve this challenge and achieve interactivity, in our work we took a fundamentally different approach. We abstracted spatial aggregation queries as graphics operations. Essentially, we observed that the spatial join between a point dataset and a polygon dataset can be considered as drawing these two datasets on the same canvas and then observing their intersections. This is just a high-level idea, of course. You'll understand it better when I explain more. But why this is important is because converting spatial joins to drawing operations is what allows us to achieve interactivity, because drawing operations are highly optimized for graphics hardware and thus can be performed very fast by leveraging the graphics pipeline of the GPU. Now, when we are drawing on the GPU, we do that on a pixelated canvas. So we don't have a white canvas, but we have a canvas with little squares that we call pixels. Now, let me start drawing. In the first step, our approach that we call raster join draws the point dataset. So here I draw my first point, and as I'm drawing, I can keep track of the points that fall in each pixel of my canvas. So here I have one point, and I have a next point that comes over there. Again, I keep track of it. And yet another point comes in. And when I draw it, I can see that I have drawn something else in that pixel before. So I just need to keep accumulating. So my count now increases to 2. And once all the points are drawn, each pixel of the canvas maintains the aggregate of all the points that fall in that pixel. Now, in this example, I'm using a simple count of points as my aggregate function, but you could also use a different function and different aggregate function, like, for example, the average or the sum of an attribute that is attached to your point. Now, what we actually want, though, is to find how many points are inside each polygon, which we don't have yet. And we can compute that by drawing the polygons on that same canvas. So here is a polygon, and you can think of the drawing as painting all the pixels that are covered by my polygon. So here I start painting the pixels, and as I do that, I aggregate the partial aggregates that these pixels contain. So the first pixel has nothing in it, so I have a count of 0 for my polygon. Now I painted my next pixel and I found a 2. I add this to my polygon counter. I keep painting. There is nothing again, so my count doesn't increase. Now it increases to 1. And I continue. And once I have examined all the pixels that are covered by my polygon, I get a total of 15 here, and this is the aggregate result for that polygon. Now, our approach frames the problem of evaluating spatial aggregation queries as drawing operations that are highly optimized for the GPU. Also, we encapsulate both the join and the aggregation in a single operator here, and this means that we avoid join materialization costs. So we do not need to explicitly store the result of the join and then use it to compute the aggregation, but we do both operations on the fly. And finally, the drawing operation takes care of finding all the points that are inside each pixel and all the pixels that are inside each polygon. Therefore, we do not need to perform costly point-in-polygon tests to map points to the polygons that contain them. Now, you might have observed here that we in fact performed the aggregation over this purple pixelated polygon and not exactly over the original polygon that's shown here with a black outline. And as a result, there might be some points that are counted in the aggregation even though they lie outside the boundary of my original polygon. Now, generally in visual tools, such errors might not be a problem at all if they are not really visible to the human eye. In addition, in practice, some amount of fuzziness is accepted around the boundary of the polygon. And this is because region boundaries are not exact. To give you an example, in New York City, the boundary between two neighborhoods is usually a street. So you can essentially consider the whole street with its whole width to be the boundary rather than a one-dimensional line that strictly separates the two neighborhoods. So that means that essentially, if the distance between the approximate pixelated polygon and the original one is not greater than the average street width, then for my analysis that is typically sufficient. Now, I'm not going into details here, but essentially our approach measures the distance between the approximate and the original polygon and can guarantee that it does not exceed a user-defined bound. Essentially, this bound determines the pixel size. So as you modify the bound, you can make your pixels smaller, and then they will approximate your original polygon more closely, and you will get higher accuracy. Now, what also happens, of course, is that drawing at a higher accuracy might be slower, so you are essentially trading response time for accuracy here. Now, even though some approximation is acceptable in most cases, there are applications that require an accurate result for a more in-depth analysis. Now, we can still exploit the graphics pipeline to compute an accurate result. The key insight here is that errors happen only at the boundaries of the polygons. So let's identify these boundaries and then do the costly point-in-polygon tests only for points falling on the boundary. This is a hybrid approach that combines drawing with a few point-in-polygon tests to achieve accurate results. As expected, it is more costly compared to the approximate approach due to the need for identifying boundaries and performing point-in-polygon tests. Let's have a look at some results. In this experiment, the executed query counts the number of taxi rides, which are points, within each neighborhood of New York City, which is a dataset that consists of 260 polygons. We ran all the experiments on a laptop, and you can see the hardware setup on the slide, and here you can also see some configuration parameters. Now, in this experiment, we compare both versions of our raster join approach. That means the bounded raster join, which is approximate, and here we use a distance bound of 10 meters, and the hybrid raster join, which computes accurate result. And we compare them with a baseline that we implemented based on the state of the art, also on the GPU. And this baseline is also accurate. Now you can see the results in this graph, where on the x-axis we vary the input size for the point dataset in millions of records, and on the y-axis we measure the execution time in seconds. And what you can see here is that the bounded raster join is 4 times faster than the GPU baseline, and this is because it completely eliminates the costly point and polygon tests, which the baseline has to perform. And what's even more interesting to see is that here, even for the largest input size of 850 million records, the bounded raster join takes roughly above 1 second to execute. So that's a good speed for interactive applications. Now, let me also say that this time that you see here also includes the time to transfer the data from the main memory to the GPU memory. So if we actually now look at the breakdown of how much time it takes to transfer the data and how much is the pure processing time, we can see that in the case of the bounded raster join approach, the transfer time actually dominates or is at around 50% of the overall execution time. Now, we expect that as we are getting faster interconnects from the main memory to the GPU, this transfer time will naturally decrease, and so will the overall execution time of this approach as well. And this brings me to the end of the first part of my talk, and this is the take-home message from our work on interactive spatial analytics. In this work, we decompose spatial aggregation queries into graphics primitives, which enables us to use modern GPUs, evaluate queries on the fly in real time, and trade accuracy for interactivity. That way, we enable city planners to interactively navigate urban data and thus for more informed decisions. Now, if you are interested to learn more about our work, here on the top of the slide, I'm also highlighting some relevant publications. Now, let me introduce you another simple approach that we proposed to accelerate spatial queries. Now, in spatial databases, objects are typically grouped together according to their spatial proximity, and then they are collectively represented by the minimum bounding box that fully encloses them. Here is an example on the slide where the gray boxes are the objects that you have in your dataset. Here they are 3-dimensional, and then the big box with a black outline that you see around them is their minimum bounding box. Now, the problem is that when you have real-world data, this minimum bounding box can be a rather bad approximation of your spatial objects. And as a result, you can see that there can be a lot of empty space inside the box that is not covered by any object. In fact, in some experiments we did using a neuroscience dataset, we observed cases that even up to 97% of the area inside the box was actually empty. Now, this is a problem because the reason we have these boxes is to use them as a fast filter to identify candidate query results and therefore execute queries faster overall. So This is an example spatial range query that I show you here with the red color, and this query says, find me all the objects that are inside this red box. Now what we do is that we first test the minimum bounding box for intersection with the query, and only if these two intersect, then we are going to examine all the individual objects one by one to see if any of them is inside the red box. Now, as you can see here, this empty space inside the minimum bounding box results in ineffective filtering, because here there is no object inside the red box, but because that red box intersects with a minimum bounding box, we think that there might be, so we need to test all the objects. And that slows down our queries. So to address this inefficiency, we proposed to clip away or subtract the empty area that's situated around the corners of the minimum bounding box. The resulting shape is what we call a clipped bounding box, and as you can see, it is essentially our original big box minus some smaller boxes that are subtracted away from around its corners. Now, by doing that, we can approximate our underlying data more efficiently and more closely, and have better pruning power. And as a result, in our experiments, we saw that we can answer a spatial range query on 1 billion objects in less than 200 milliseconds. In the last part of my talk, I will discuss a little bit my current work, which revolves around Earth observation data analytics. With the recent advances in satellite technology, Earth observation data archives are growing at an exceptionally fast rate. For example, the Copernicus program, which is the European Union's flagship Earth observation program, has Sentinel satellites that acquire roughly 12 terabytes of images per day. As a result, in 2021, the total size of the archive reached 20 petabytes, as you can see on this graph. This wealth of satellite data represents a unique opportunity to deliver significant impact in different applications, such as agricultural monitoring, water bodies monitoring, again, urban analysis, or even climate change research. Now, to enrich data science applications, researchers and practitioners combine satellite data with a variety of other data sources, such as data from sensors and IoT devices, social media data, demographics, administrative boundaries, and so on and so forth. Now, these datasets that I just described come mainly in two different forms. From the one side, we have satellite imagery that conforms to the so-called raster data model, and from the other side, we have spatial data like region boundaries that conforms to the so-called vector data model. As I said, there are many meaningful queries that combine data from both data models, such as simply finding the average precipitation, which is a raster, in each city, which is a vector. Now, the slide here shows you how a vector and the raster data model look like. The vector data model represents spatial features with their geometries. Typical geometries can be points, like, for example, a GPS location, lines like roads or rivers, and polygons that can be region boundaries. On the other side, the raster data model represents the study area as a collection of pixels, where each pixel is associated with a geographic location, and satellite images conform to the raster data model. Now, traditionally, we have systems for vector data, we have systems for raster data, but we do not have systems that natively support the two data types together. Therefore, to answer queries that combine both data models, we need to transform the vector data to a raster format and process everything in a raster system, or the opposite, right? Transform raster data to a vector format and process everything in a vector system. Now, the problem is that both transformations are very costly. However, currently, such transformations occur very frequently in data science and ML applications for Earth observation, as they need to combine multiple datasets of both representations. Now, to understand this problem better, I worked together with some students to develop a benchmarking framework that allows comparing spatial systems that join raster and vector data. The first step is to select meaningful datasets for the benchmark. So we collected different open raster and vector datasets, analyzed them, and grouped them based on different characteristics. Now we give these datasets as input to the benchmarking framework that we developed. The framework also allows defining parameters for the benchmark run and different queries. There are different parameters that we can define, like the number of times that the benchmarking experiment should be repeated, or whether we want to include pre-processing steps in the benchmark. The queries that we run contain a join between a raster and a vector dataset that we specify, but they can also include selection and aggregation operations. The framework also allows selecting the spatial systems to benchmark. Finally, the benchmark framework runs the benchmark based on the specified input. During the run, it records metrics that capture resource utilization and markers that capture the runtime of different stages in the execution. Furthermore, the framework gathers the results of the queries produced by the different spatial systems in order to perform an accuracy analysis. This is necessary because systems might lose accuracy in the process of converting raster to vector data, or vice versa. Here are some results of an end-to-end benchmark that we executed using our benchmarking framework. Here we join three cadastre datasets, specifically borrow, usage, and plot usage, with satellite images from Sentinel-2. And you can see the hardware setup here on the slide. Now, we also have a little bit of more information about the different datasets in these tables. Now, on the graph, on the x-axis, we have four different spatial systems, and then we also have three groups, where each group corresponds to one of our cadastre datasets, so borrow usage and plot usage. And then on the y-axis, we measure the runtime in seconds. Now, this runtime, we split it into two parts, the actual execution time and the data ingestion time. I won't go into all the details of the graph, but one important observation here is that when using a database management system like PostGIS, which is the system that you see with the orange color on the graph, then the data ingestion time actually dominates the overall runtime. And so there are several open problems that I'm currently working on related to how we can make Earth observation data analytics more efficient. So the first one is an ongoing effort, and is what I already presented. So how can we establish a systematic benchmarking framework for heterogeneous spatial data workloads? And I just presented some initial results. Now, as we just saw in the last experiment that I presented, ingesting data into a system can be a significant overhead. So naturally, the next question is, how can we reduce data ingestion overheads in spatial data management systems? Some ideas here are to load data into the system incrementally as a side effect of query execution. To perform this incremental loading efficiently, we can index the structure of commonly used file formats so that when we access these files to load the data, we can do that fast and efficiently. Then, once we have the data in the system, the next question is how to join raster with vector data efficiently. And my idea here again is to avoid an a priori data transformation and instead use an adaptive indexing technique so that only the data that is needed by the queries is indexed and transformed. Furthermore, like we did before with the raster join approach, we can relax the accuracy requirements and first compute an approximate result fast. And then if it is really necessary for the analysis, we can spend some more time to refine that result and make it accurate. And this brings me to the end of my talk, and I will take one last minute to summarize the main points. In the first part of my talk, I showed how to decompose complex spatial aggregation queries into graphics primitives, which enables us to leverage advances in computer graphics to attain interactive speeds. Then I talked about the inefficiency of combining raster and vector data. On that front, we are working on developing comprehensive benchmarks to understand what is possible to achieve with the current spatial systems. Furthermore, one of the main bottlenecks in combining raster and vector data is the transformation from one data model to the other and the data ingestion into a database management system. Therefore, we need to design approaches that do these steps selectively, driven by the actual workload, so that we only transform and ingest the data that is really used. So, thanks a lot for listening. And before I finish this recording, I would also like to say that I've done all this work together with some great collaborators, mentors, and students. And you can see their names and the different institutions where I have worked on this slide. Thank you.